I'm back. So today we're going to be, instead of doing the competition math problem, we're going to do another fun video that kind of incorporates physics and also some differential equations. So let's start. First, let's start with a really important equation in this episode, but also an equation that's like really just basic in physics learning, which is just F is equal to ma. Well, this one is basically just saying that, well, actually there's to be more official, there's an arrow here, which force is actually a vector and acceleration is also a vector. So what is A? A is basically when we have an object that moves in a velocity, then at this time the velocity actually changes to be either smaller or just larger, or oopsies, I just clicked something wrong, or just like moderate larger, or even it changes the direction. That is also a type of acceleration. Force is basically the thing that causes the acceleration, because we can see that m is actually just a scalar quantity. So this basically means that force is proportional to the magnitude of acceleration. Alright. We introduced this really important concept, and now we're going to deeply dive in what is acceleration. So let's say if I have a graph that is oriented as velocity and time. Time is just simply the normal time constant, which is just in seconds, and velocity is just in meter per second, to simplify. Okay, so let's say if I have a graph like something like this. So this basically means that at each point this is actually the time, and this is basically the velocity at this time. So essentially, this is basically the instantaneous velocity at this time. And now let's see. Now let's say if I just choose random 2 points, say this and this, because we also know that A is equal to velocity over time, actually change in velocity over change in time. So essentially, if we incorporate this in this graph, then we can see that this part is basically changing time, and this part is in change of velocity. Well, I'm pretty sure that if you guys learn about calculus, then this will be included in one of the episodes, which is actually pretty widely used to illustrate the idea of a derivative. So let's just remind us what derivative is. So basically, derivative is basically just the slope of the tangent line at a point. So in this case, if we take the derivative of this, then this slope would actually be the slope of the green line. And on the other hand, the derivative will just look something like this if we take this in the left point. So we can see that this one's actually more flat than this slope. Okay. Now, basically how they do it is we just move this point toward this point. Or if you want to take the derivative at this point, move this point toward that point. So as we move this closer and closer, like let's say here, well, here is definitely more closer than this point. Then when we connect these two, then this seems to be actually pretty close to the actual derivative line. And now we even move it closer and closer, like just tiny bit away from our target point, then this will just literally be almost the tangent line. So essentially, this one can just be expressed as the limit as h approaches to 0 of, or let's just say v of x, v of t plus h, because we always use v of t in physics, minus v of t, and divide by h. Well, you might be asked, well, when h is 0, then this one just undefined, but actually we can cancel out the h based on the top. Okay. But in order to interpret this one, it's basically saying that, well, we can just say that if this is actually t, and this one would instead not be delta t, but be h in the context of our limit. Okay. So basically, this point we can see is just v of t plus h. So basically, the limit as h approaches to 0 basically means that we'll keep moving this point closer and closer to t until it approaches to be 0 away from the point that we're targeting. And this one is basically just the expression of acceleration. Now, in terms of derivative, we can just express this as dv over dt. Okay. So now we're going to consider a scenario that might be an application to this one. So let's say if I have a ground, okay? So the ground, so we actually have a coin or like a ball right here, which has a mass m. And now we're dropping. However, in the real world, the situation do not always act as our preference, because there's actually a velocity. No, there's actually a resistance force that acts upward. And we obviously just have an mg. Just call it Fg. And we have an F resistance, AR, I just call it. So now let's try to think of what is the magnitude of F of AR possibly be. So if we have like something like an air right here and the ball is moving down, then we can see that at the surface it's actually pressuring the air. Now, if we pressure the air by Newton's third law, then this basically means what? It basically means that there's actually going to be a resistance force that has an equal magnitude, but it's also going in the opposite direction of that, such that it actually opposes the motion of this ball. So now can we think of what is the possible magnitude of this force? Well, it will just be F is equal to kV, which K is just possibly a constant. Okay. So now how can we possibly set up an equation? From Newton's second law, we have net F is equal to ma. Now what does this tell us? This basically gives us mg minus kv, or kv is just from the equation that we just derived. That is equal to ma. Now we can see because the velocity is actually changing, therefore it would not be a good idea to just divide by m. Now, let's remind us what a is. A is just dv over dt. right? Yeah, it's just dv over dt right here. So therefore, because it's dv over dt, we can just substitute back in. So we have mg minus kv, that is equal to m times dv over dt. Now I can divide m to the other side. We have g minus k over m times v, that is equal to dv over dt. Aha, this one's just a differential equation, and because we can just write this one as a function of velocity, because we know that k and m and g are all constant and known. So, oopsies. So therefore, from this, we can literally just solve this differential equation. So we divide, we have dv over g minus k over mv, that is equal to dt. Now we simply just integrate both sides. Then we actually have, let's just call this w from our w sub technique. Let g minus k over m v equals to w. Then we know that dw over dv, that is just equal to negative k over m. So basically we have dv is equal to dw times negative m over k. Substituted back in, we actually have negative m over k, excuse me. So we have negative m over k times the integral of 1 over w dw, that's actually equal to t, because the integral of t dt, or t plus c, don't forget the plus c, and well, this one is just equal to ln w. So this one basically just gives us negative m over k ln of w plus c1, that is equal to t plus c2. Now just move c to the other side. Now move the c to the other side, we actually have negative m over k ln of w, that is equal to t plus c. C is just a constant. Now we raise everything to the e's power. Well, actually we can just multiply this to the other side. We have ln of w, because we know that g minus k over m times v, that is always positive, so we don't have to worry about the orientation. So no absolute value is needed. So now this is basically equal to negative k over m t plus c, which c is just another constant, so we can just incorporate that into a constant. Now we just rise to the e's power. So we actually have w is equal to e to the negative k over mt. We just move the c to the front. Okay, so from that, when w is equal to e to the negative k over mt plus, well, let's just say that this one is just e to the negative m over k plus c's power. Now, don't forget what m is. M is actually equal to g minus k over mv. And we essentially want to find v, the velocity. Therefore, this is actually equal to e to the negative k over mt c. So we want to find velocity, so So essentially it's just G from that we just simply multiply by m over k. V is equal to m over k times G minus e to the negative k over mt plus c, and that is essentially our answer. So from this episode, we actually see that how everything just simply incorporates each other. We simply start from this characteristic equation, and we also dive into the air resistance, and we just derived a formula for velocity of ball dropping in the actual scenario using these knowledges. Thank you for watching. Hope you enjoyed. That is all that I prepared for you today, and I'll catch you in the next video. Goodbye.